Today we are covering the stability of anti-aromatic compounds. So we all know that anti-aromatic compounds are highly unstable species which has 4 and pi electrons. Now at below minus 50 degrees Celsius, the anti-aromatic compounds are far more stable. So if you ever encounter an anti-aromatic compound, by X-ray diffraction method it was found that the anti-aromatic compound, for example, cyclobutadiene, is a rectangular molecule. A rectangular molecule means that this bond length and this bond length are different from one another. That means in this case the resonance is not possible because resonance causes the all bond lengths to become equivalent. This is a proof, the very proof that resonance is occurring. But at minus 50 degrees Celsius, it suggests that the temperature is such low that the delocalization of these pi electrons is not feasible. And because of this, at minus 50 degrees Celsius, cyclobutadiene exists as a non-aromatic compound. It is non-aromatic compound. Now, even at room temperature or at minus 10 to 20 degrees Celsius, the thermal energy is enough, sufficiently large to cause the pi electron delocalization and turn it into anti-aromatic. But it becomes so much unstable at the temperature that it undergoes dissociation, converting itself into a biradical form, combining with itself and to give us a dimer at any temperature which is greater than minus 50 degrees Celsius. So now the question arises, since we know that anti-aromatic compounds are not stable, and the very start states that we are talking about how to make them stabilize. So the thing is, anti-aromatic compounds are not stable enough. So here what we are trying to do is we are trying to keep them stable enough that they can exist at room temperature. Or let's say somewhat low temperature below it. This is what we need to prove. Now there are multiple reasons that you can use, multiple things that we can do. For example, if I encounter this particular compound, the anti-aromaticity arises because of two reasons. Number one, the 4 and pi electrons that it contains. Second, the 4 and pi electrons it is contained, and second one being the anti-aromaticity, or simply the pi electrons, simply the pi bonds or pi electrons. So if I convert it to a 4n pi electron system to 4n plus 2 pi electron system, I can convert it from an anti-aromatic to an aromatic compound. Second thing, I can remove any excess pi bond, which can lead to, if I remove one of the pi bond, you can encounter that this will become a 2 pi electron system, which will again get to this particular point. So the method that we will be utilizing, first method is called as, first is using bulky substituent, using bulky substituents. So if the pi electrons that you are taking part, which are responsible for the dimerization of the molecule, if for some reason I can make the other molecule, previously we have taken two different biradicals which are combining together to give us the dimer. So if for some reason I increase the bulkiness around the pi bond so much that no two dimer can interact with themselves, and this can lead to stabilization of the molecule. This can lead to the stabilization. Now it can be stabilized close to room temperature or at much lower temperature, which is greater than minus 50 degrees Celsius. So first option is this one. Second option we can go for is removal of pi bond. Removal of pi bonds. Now there are several ways. Number one, making a dianion. Dianion. So if you have any anti-aromatic system and it has hydrogen right here, if I make it react with strong reducing agent like any metal, it will release two electrons, converting the pi bond into dianion form. Each one will release one electron, making the radical into a negative charge species N. Now it will become a dianion. Then, or you can use a very strong base which can abstract this acidic hydrogens and can form a dication. Sorry, not dication, sorry. This still be a dianion. Now, since you have a dianion, you can use another metal which can stabilize it. For example, you can use Mg2 plus or other metal centers of some N charge which can stabilize it. Hence, it can lead to the stabilization of the anti-aromatic ring by converting it to a dianion. Second option that we can look for is to form a dication. Dication. Dication can be formed by simple oxidation of cyclobutadiene, converting it to a dication. And the dication can undergo delocalization throughout the ring, and this 2 positive charge can be stabilized by large anions such as sulfate ions, perchlorate ions, or even oxalate ions. Third option that we have, it's called the captodative effect. Captodative effect, which also goes by the name of push-pull effect. Push-pull effect. In push-pull effect, we are using resonance and various substituents attached on the cyclobutadiene or anti-aromatic systems, which can lead to the removal of these pi bond. So, we are taking NET2, NET2, C double bond O, ET, and opposite to again C double bond O, ET. Now, here, if you look at one of the group which we have the basis Ne2, they will use its lone pair, transferring it to the pi bond, which will transfer the negative charge to the carbon side and will be stabilized by the resonance in the carbonyl bond. So here, the nitrogen here is pushing the electron and it is called the push effect or the push group, while this group is accepting or pulling the electrons from the ring, and this is applying the pull effect. Same will happen from this side. This will apply electron density, this will move, and this will take it back. And this will result in, this will be the pull effect and this will be the push effect. And when this will occur, the entire molecule will look like this, where the molecule is stabilized by resonance and the negative charge, and same will be the case for this one, NET2. So now internally this molecule is neutralized and the pi bonds which were responsible for the anti-aromaticity of the molecules have been eliminated. So these are several ways which you can use to stabilize anti-aromatic compound within a definite range. But remember, anti-aromatic compounds are always unstable no matter which state they are in. So what we can do is we are trying to increase the window frame in which we can keep them stable, or that increasing the temperature range where they can be stable or can be studied better. So that's all for now. I hope you learned something new today about the anti-aromaticity and how to stabilize the compound. In case of any doubt, you can add it to the comment section or any new topic you want us to make the videos. That's all for now for today. Thank you for joining us.